This happens a lot. This is the rule, not the clonal pathogens. So in real life, in real nature, in forest, coral, reef world, this is what you see a lot of. And the clonal pathogens, while we focus a lot of those in clinical medicine, this is in fact what happens most of the time. So an important part of this concept of diversity in bacterial genomes, we like to divide the regions up into two categories, what we call the core genome versus the accessory genome. The core genomes are, just a simple definition of the core genome is any genetic material that is shared by all the members of the sample set that you're studying. You can think about this as being the essential genes or the housekeeping genes that have to be present in any genome for that particular organism to function. But again, the practical and usable definition is just, are they there or not? We use the core genome almost exclusively for constructing phylogenetic analysis, one, to avoid having missing data points in our data matrix, but also because we think that they are less recombinogenic. So these accessory genome elements include things like phage, transducing particles, recombinational things, or, as I'll show you in just a second, regions of the genome that have been deleted out because they're no longer needed. And so that accessory part of the genome becomes very complicated in a phylogenetic analysis. So just to give you a little bit of a tip where I'm going with this, in the core genome, we try to score SNPs, single nucleotide polymorphisms, because they're stable and revert very seldomly. There's a lot of them. There's a lot of real estate in the genome. And the accessory genomes we segregate off. And then once we've constructed a phylogenetic tree based upon the core genome SNPs, we will then map these accessory genomes back onto that phylogeny. Lance showed a great example of mapping that phage back onto the ST398. And so that's the type of approach that we take with all of our bacterial pathogens. Now when I think of the genome, I first think of core genome and accessory genome, but I also think about how fast it evolves, because not every nucleotide in the genome is equal, and they evolve at much different rates. Again, 10, 15 years ago, we were struggling to try to understand bacterial populations, and we started to focus in upon hypervariable or highly mutable regions like VNTRs. And so VNTRs in this region mutate in this region really fast. Lance, in fact, was one of the first people ever to discover a VNTR in a bacteria and coined the name multi-locus VNTR analysis for that. So this was something that we could use to identify variation or discriminate between different isolates in very young populations. I mean, so young that you might be looking at isolates from a single person or a single outbreak. And so that was essentially the way that we did that. And then there are more complex things, the PFGE, which I've been bashing already in this talk.